Okay. Last talk of the day. So I have here Nins, who's a software engineer that's transformed, metamorphosized into a machine learning engineer, and has recently finished his master's of research with a focus on agriculture and image processing. So he's going to be talking to us today about a simple way to validate and monitor the performance of ML applications. So round of applause, please. Thank you.
Hi. Hello. Hello. Can you hear me? Okay. It's nice to be back on a live event. Hi, everyone. First, I want to thank PyCon Australia for organizing this event. Definitely a good one for all of us, right? So for today, I'm here and I'm gonna talk about a simple way to validate and monitor the performance of your machine learning applications. Okay. A little bit about myself. I'm Nins. I do mountain bike. I love Dota 2. You can talk to me about software engineering, data science, machine learning. I love to lay on grasses, as evident by the picture. And I like custard buns. You know custard buns? It's really good. Anyway, let's go. So for today, I hope I can impart some learnings to you guys, and I hope you learned a lot from this session. We're just going to briefly go through and talk about these points right here. So first one, let's try to identify what is model validation in the context of an application or a machine learning application, to be exact. Right? So how do we identify the trends? Why do you need validation? Specifically right now, people are always into, most of us are most into AI because of ChatGPT and stuff, right? So how do we choose the correct validation metric? What are the available metrics that is in store for us? Let's try to build a simple model validation module in Python. So I'm going to show you an example of one of the simplest ways that we approach this problem in my previous work, and I'm still using it as of today. And then we're going to briefly talk about retraining and model maintenance. So stability versus retraining, and then how long does your model stay in production, and the maintenance cost of those models. Okay? Now, every time I start a machine learning project or I talk with data scientists, I always ask these questions. Right? So we always discuss if there's any ground truth validation data available going forward. How can we validate the results of the model? What metrics do we use? As I mentioned, we're going to go through this later. Is there going to be a change in the distribution of the features? Or are there going to be changes in the relationship between the features and the target? Right? So when I deploy the application, will the deployment environment change over time? So lastly, we always talk about, with the data scientist I'm working with, we're always like, how do we retrain the model? How do we adjust the model? How can we make sure that the model is always, performing at its best? Now, let's talk about performance change. I believe there's going to be a very specific talk about this tomorrow. So we're just going to cover some of the basic and the underlying concepts with this. So model performance change, it decreases over time. It's almost always the case. So it can be a result of several factors, mainly if it's a concept drift, so the nature of the problem changes, or if it's a data drift, then the distribution and the relationship between the data changes. It happens most of the time. It can be an actual deployment setup problem, right? So someone accidentally pushed a new version of NumPy in the requirements.txt, and the performance changed. Models are always going to be performing at its best right after training. Once you deploy it, that's its peak, right? Unless you retrain it, because it's going to encounter a new data set eventually. Right? And sometimes these changes can cause unintentional bias, which is not bad, because in some context or in some problems, putting in bias is actually quite good, right? It depends on the context, it depends on the problem. Now, just a brief preview about concept drift. It typically involves the problem that the model is trying to solve, and suddenly it changed, right? So I drew that graph. I'm not sure if it's good or not, but it's cute. So here we can see that initially the model is predicting the data points in blue correctly. The data points in orange are the ones that we used for training. And then suddenly, something happened, right? It's misdetecting everything. So these things actually happen in the wild or in the development environment, in most development environments that we have before, right? One example would be COVID-19 trend prediction, right? When a variant change, or if there's a new variant, essentially it's gonna have a different interaction, right? Transmissibility will change, other factors will change. So essentially, you're not predicting for the same problem anymore. This could happen suddenly, like this one, or it can happen gradually, incrementally, or it can be recurring. Sometimes recurring concept drift happens in like weather data set. It's quite common. But I think the most common one is the gradual, because sometimes you don't notice it that it's happening, and then suddenly the entire problem changes, and your prediction changes as well. Right? There's also data drift. So I think this is easier to understand. It basically means you created a model using a certain set of data range or data distribution, and then as you go forward, new types of data distribution occur. Right? So this is very common in financial models or in demographic type of data. Right? So if you're dealing with this problems right here, you can expect to encounter this. And it's usually easily fixed by just, retraining the model again. So we'll discuss more about retraining later. Now, why is it important? So, Morty, I'm a fan of Rick and Morty. Detecting and identifying this change or these trends in terms of the performance of the model is actually quite important, because it's a good indicator of your machine learning application. It's a good indicator how it behaves, right? People talk about trying to make sure that their machine learning applications perform really well over time. Detecting these changes are a good indication of, what's happening in your application. So understanding these changes also lets you efficiently make decisions in terms of retraining, adjustments in your model, especially when we have this project before wherein we're trying to do a factory line. So you need to predict really fast, and then you need to retrain really fast, something like that. So if you understand how the performance shifts, you can easily retrain based on the parameters that you want, etc., etc. And I think one of the most interesting things that can happen is that you are able to understand more of the data set, right? If you are able to detect this change in the model performance, then some new patterns arise, some new features can be extracted and stuff like that. So this is quite interesting. This is part of feature engineering. This is quite interesting that it shows up once you understand how your model performs, right? So as I mentioned earlier, here we have an example of fixing a data drift. So the initial training data is limited, and then as we move forward and encounter new predictions, what we can do is we can adjust the training data to include the new data set that we encounter in order for us to correct the model. So here you can clearly see that, the model adjusted if you include more training data set, right? Now, how do we measure the model performance? Let's just go through this briefly. It depends on the problem, right? So I'm sure at least most of you might be familiar with regression and classification type of problems. So depending on the problem, you might want to use this, like mean square error, root mean square error, and similar approach if you're dealing with regression problems. So if you're dealing with classification problems, then you typically use your accuracy, precision, recall, F1, ROC, AUC, and stuff like that. But what does it mean, right? Let's say, for example, I have this performance trend right here. I'm measuring two metrics, which is accuracy and recall, for example. Initially, the recall started really high, but then at some point it went down, while the accuracy went up. Which metric should you use? Is it accuracy? Because, over time it goes up, or is it recall? It depends on the problem and on the context of the problem. Right? There are some instances that it's very important to know. Like, for example, when recall, it's being used for medical data set, when you're not, it's okay for false positives and stuff like that. So accuracy, there are also certain types of problems that you might want to prefer accuracy or F1, right? So it depends on the circumstance. And in our use case, and in my experience, typically, when we're trying to monitor the performance of a model, we use 2, 3, 5 metrics at a given moment, at a given model. So it's not just one, it's not just two. Like, minimum 2, yes, but then the more the merrier in this case. Or, the more you use, the more metric you use, the more information, and the more you understand the behavior of the model. Right? Now, how do we build a simple, that's the key term, a simple validation module? How do we integrate this in our application? So there are several ways for you to be able to detect data drift and concept drift. There are statistical tests. Those are quite technical, right? And some of us don't want to deal with those kinds of numbers and those approach. There are several drift detection algorithms, but typically they happen on, you need lots of data set to be able to understand it. We want to be able to detect these changes on the go as it happens, right? It needs to be simple so that it can be integrated into any kind of application that we want. And the model validation function should be easily understandable because for developers, we want maintainable and easy to understand code. So, show me what you got if you're familiar with the reference. Anyway, yeah, that's the thing. We need to catch the early signs. So if you look at my poorly drawn graph right there, we need to catch those instances, the one that's encircled, those data points, right? What we learned when we're building these machine learning applications, we need to regularly check for performance change. There are applications that we have, I don't know, maybe every 5 minutes we try to see if there's a performance change because it's running 1,000 predictions every second. So, And then one of the things that we learn is that let's just assume that the outliers are wrong prediction. Okay, I have no bad blood versus outliers, but in this instance, it's safe to assume that there's something wrong with these outliers right here, and we want to understand why are they outliers. So, yeah, just assume they're wrong predictions. Okay. The next step would be to prepare a good validation data set. I will show you a simple diagram later, but essentially, it's different from your testing or training data set. These are data set that you can anchor to the model, that's the term that we're using, or that you can attach to the model, to the deployed model, so that you have a consistent understanding of their performance. We're going to see that later. And ideally, you should have a secondary model, a stronger, more powerful model for automated validation, or sometimes we do, actually most of the times, we do manual validation of sampled incoming data so that we're sure that the application is performing really well. And it's very useful in terms of retraining or creating a new version of the model. Now here's a basic overview of what typically happens during model development and deploying it into an application. So initially, you have the model development, which is the data scientists are involved, the machine learning engineers are involved, and they're using training and testing data set to be able to create the best model or to be able to produce the best model. After that, we're going to use that model in an application, and typically we record, or no, you should record the results in the database, or you should keep track of the results of your model. That's the key part right there. Okay. And then lastly, we have two ways, in most of our applications that we built, we have two ways of model validation or checking the performance of the model. So one is using the validation data set, and the other one is double checking the incoming or the new data that we encounter, or the model, or the new data that the model encounters. Now let's just take it slow. Maybe use this as a good storytelling stuff that we're gonna go each step. So first one, data scientists, machine learning engineers typically create a really good model using testing and training data set. I think most of us are familiar with that step. After that, what we typically do is we prepare a separate validation data set. Okay? And then we place that model into a controlled environment that's very similar to production, ideally. And then we run the validation data set several times on the model. Maybe if you're using k-fold or any kind of sampling, whatever, it's up to you. So we run it, and then we record the results. After that, we have this, we have this acceptable result metric that we're basing, or that we're recording. So in this instance, for example, this application setup paired with this model, paired with this validation dataset, should produce an accuracy of 80 to 82% and an F1 score of 80 to 81% with 100 predictions in 10 seconds. So you see, we're trying to figure out the constraint of this model in this given environment. So take note of that. Take note of that metrics right there. So we typically record it, right? And then we deploy the model in the application production setup. So the model does its job. Users use the application. The model does the prediction. It stores it into the database, and After that, we want to identify if the model is still doing well as we use the application. So again, we're going to go back to the initial approach right here. Inside the application, we have the validation data set, and we will apply that validation data set to the model, and we will check if the result is still consistent with the recorded results that we have from our testing. Right? So here is a very simple Fast API example. Some of our microservices are built in Fast API. So we're just using the repeat decorator, and first thing that we do is we load the validation data set. After loading the validation data set, we perform the prediction on the validation data set. So it's here. Oh, it's cool. You can see it. Anyway, we record the start time and the end time just to get the duration right here. And then we basically get the F1 and the accuracy, or whichever metric you are using. Now after this, we're basically just comparing if the accuracy, F1, and duration is still within this range, right? So every time that this validation runs, in this case, it's running every day because the frequency is per day. So every day, it should always fall into that bounds, right? If it's not there, or if it decreases, if it increases, something might have gone, wrong, or something might have changed from the setup. Okay. So what's it for, right? Initially, when you look at this setup, it seems pretty trivial because you're just validating it against itself every time. What are we gaining from this, right? First is it's quite simple. You can implement it in most of your applications easily. Straightforward. And it's flexible enough to support multiple validation metrics. Okay. However, what we discovered is that implementing this very simple function can catch or can identify if there's a change in library or a dependency version, NumPy for example. One specific example is that we have an application deployed in an EC2 instance. And for those of you who are familiar, sometimes Amazon they sometimes update the VMware that's underlying the EC2. That's quite annoying. So you think that there's no update, but they update the underlying architecture of the VMware, which changes some of the libraries, especially when you're using deep learning and stuff like that. So our results suddenly change, and we're like, what's happening? What? Did something change? Did someone push something? So that's one of the use cases. It's actually very useful to detect if the setup has changed. There are some instances that the parameters of the model change when someone push a new code or when someone creates a bug fix and stuff like that. Sometimes they accidentally change the parameter of the model, so we can detect that change as well. And when you have a device set up, if you're using hardware in your prediction, this is definitely useful because you don't know if the hardware is broken and if it's deployed somewhere, if someone tampered with the hardware, if the resource is not enough. So that's the goal of the first validation, to detect these kinds of change. Okay. Now let's go to the second step, right? So we have our application right here, and our really good model didn't do so well on some of the data points, right? So he's like, I'm not sure, maybe I'm just 50% sure of this, maybe I'm 70% sure of this, I'm 63% sure of this, and stuff like that. So in classification problems, there is a predict probability, which is this one. So this is an example of some results using a classification problem, right? And then our little model right here is not sure. I don't know, but maybe this is true or maybe this is false. So we record the results, right? Even the probability, we record it every time it performs a prediction. Now we have the probability. We have two ways of going around this problem. The first one is we have this big, bad new model right here, right? So this is often our secondary model. In our deployments, we always have 2 or 3 models in place, right? So the first model is the one that we're using, the one that's actually tailor-made for that specific problem. And then we have another model right here who's probably a lot stronger, can classify better, but it's quite slow, right? So there's a trade-off. But they're still useful, right? If they can just validate some sample data, it's still useful. So that's the model, that's the validator model right here. That's what it's doing. It's trying to figure out if the results of this main model that we have, if the low confidence scores, it's trying to identify or it's trying to classify it with better confidence. So the goal is, these classifications right here should be, it should have a solid or it should be at least 80% confidence, maybe even higher, right? And if you're using this, you can do an automatic retraining if you want. Well, I'm going to show you some code snippets later. In some instances, we're working with several research groups, for example. And then when they're using their model in the application, what they wanted is they want to see the sampled data set right here. So they want to be able to see it, and they want to be able to verify it themselves. This is very crucial, especially when you're working with medical type of problem, or maybe research type, research in biology, or So they really want to see their data. They want to be intimate with their data. Right? So in this case, what we do is, after we build the application, we sample this data set right here, and then we give it to them through a report, right? And then that's it. They validate it, and then they can retrain based on it. So this is sample code of manual retraining. So we just, right here, we get the sampled result that has very low confidence score, and then basically send it to the user. Do whatever you want. Or we can go with the automated route. In this case, after we get the sampled results, right, we have a second validator that predicts the flag data set. And then we compare the accuracy or whichever metric you want to use. If we want, we can just directly overwrite the results using the more stronger model. Or we can decide on what to do. Maybe if the accuracy is this, overwrite and then retrain. Okay? Now, this is really good for detecting early signs of drifts, model drifts, concept drifts, and possible changes in the data distribution. So this is what we usually have in place so that we can identify if there's a problem or if there's going to be a problem with the performance of the model. Now, lastly, we're going to talk about model maintenance. Here, we have the concept of model stability versus retraining. Sorry. So models are more stable if you don't need to retrain them from time to time, like this one in the first model. And it's less prone to model and data drift, right? However, they might require more time to develop because you need more data set, you need to gather more resources to make the model more stable. Unlike the second model right here, where you need to retrain periodically if the performance goes down. However, you need to understand that if you retrain the model on a longer period of time, it seems that it's actually quite stable, right? As long as you have a good retraining process. And it benefits from the new data set that it learns. Okay. Now, for model longevity, like, it depends on the context and the expected inputs. If it's just a small problem, then typically you're going to have a model deployed somewhere over a long period of time because it doesn't require any change. Similar with the dynamic relationship and like if you need to retrain models from time to time, the data that encounters is dynamic. So you need to replace the model and most of the time you need to retrain them. And lastly, this is my last slide. So the cost of maintenance, you always need to consider this. If you want to produce stable models, you might have more upfront cost. Again, as I've mentioned, stable models are more expensive to develop, right? And, you know, it's always good for models that need constant retraining. It's better to automate them to reduce the cost, and you can always use transfer learning if you want. And that's the end of my slide. Questions? Hey.
Thank you, Nins. Very, very interesting, very insightful. Now, we've probably got time for some questions. I can't see anything from here.
You can see the light is so
Any questions? Oh, someone over there, I think.
Hi. You mentioned retraining the data as the model accuracy dips over time. And I just wanted to ask, how do you, like, what are some techniques you have to avoid model overfitting as you retrain, particularly with things like unidentified seasonal data and, yeah, just how you would avoid, especially when you automate the retraining process?
Yeah, I think that's a good question, and I think we get that question a lot, right? Remember in the earlier part when I told you to use more than one metric? Use 5, use 10 metrics to be able to fully understand the behavior of your data in your model, right? So, for example, this is a real-life scenario, like we have a model deployed in production, and then the F1 score continually goes down, right? It continually goes down. However, if you look at recall and log loss function, the performance is still okay, right? If we follow the F1 score, we constantly need to retrain the model. And as a result, the subsequent models became overfitted. However, we did not do the retraining because we have the log loss and we have the other metrics that allowed us to understand that, okay, it's okay if the F1 score decreases because it will be overfitted if we retrain. It's not the target metric that we want to use anyway. So, you know, that's one of the ways that we approach the problem. And I think you should have a hands-on, or you should try it hands-on so that you can experience it yourself, right? Because it's It's something that you'll definitely see in the patterns of the data once you try it yourself.
Cool.
So
Thank
just
you.
use metrics. Use as many metrics as you want. Questions?
Thank you. Any other questions? Oh,
I can see.
just one over there.
I've got a bit of a two-parter. So you mentioned the test, train, validate, split. Do you have preferred proportions for splitting your initial data set into test, train, validate?
Yeah,
do they vary with the size of the data available? The second part of my question was, it sounds like you're picking low confidence predictions and labeling those samples and using them to bulk up your data set. In production, if you're picking actual samples submitted to you, have you ever come across privacy concerns with that?
Okay, so I'll answer the distribution problem first. Typically, for example, let's say we have 100 data points, right? So typically, what we do before is somewhat 60% training data set, 20% testing, and then 20% validation. However, we discovered that ideally, we would want that validation data set to be sampled differently from the training and the testing data set. So if we have an option to ask the customer, hey, look, this is the initial data that you provided. We can train with this data set, and then we can use some part of it as a testing data set. However, would you be willing to extend your data set maybe to another month? Like, for example, if we're building an application for them, they're going to give us another month worth of data after we finish the model, and that will be the validation data set. So we figured that, or at least the data scientists in my team, they figured out that it's more organic that way. They were able to capture the relationships of the data better because, let's face it, if someone gives you a training data set and a testing data set, there will always be some form of bias going on in there, right? So they will, this is our target problem, and oftentimes they will give you a really clean or a really standard relationship between the data. So that's what we typically do. We separate the training and testing data set to the validation data set, right? So if you can do that, then do that, right? I'm sorry, what's your second question?
It sounded like you were picking low confidence predictions for production use case of the model and then including them in your data set. If you are doing that, have you come across privacy concerns, or are you just not processing data where that's a problem?
Oh yeah, so we're picking the low confidence predictions just for validation purposes, right? It's still up to the data scientists if they want to include those data points in the prediction, right? We just want to understand why these guys have low prediction scores. And if it makes sense to include them in the training data set, or if it makes sense to create a new model out of them, then of course we will do that, right? So it's not we just pick them and then include them right away. There are some instances like what I've mentioned, wherein if we're really confident with the model, like if we have a big red model, getting ready for those data points, we just overwrite them completely. But in most cases, there's always another layer of choosing which of those low confidence data points should we include in the next training cycle, right? So there are other statistical tests that we perform in those low level data points to make sure that we're including a data point that represents or has a good representation of the actual problem that we're facing. So does that answer your question?
I think it just sounds like you're not processing data that's personally identifiable, so you're free to do that, which is great.
Yeah, basically, yes. So.
Okay, thank you. I have a stupid question, perhaps.
No question is stupid.
Oh, wait until you hear it. If you've got a super brain model, why aren't you just using that in production?
Which one?
If you've got a super duper model that's like more accurate, why wouldn't you use that one in production?
Well, yeah, that's the thing. I mean, in my opinion, people are obsessed with this very generalized model that can perform everything really fast, very accurate. It doesn't exist. Not yet. Okay? It doesn't exist, or at least not yet. Right? Based on our experience, there will always be some sort of trade-offs. Like, you need to communicate this to your customers or to your partners. One example would be the factory line setup, right? We need to perform prediction on a 2 megabyte device. So it's very difficult to put in a really powerful model inside that device. Yeah, it's small memory. So, it depends upon the context, and maybe someday, hopefully soon enough, or not, we will have that really big AI that can generalize and predict most of our problems.
Maybe.
Thanks.
Okay, thank you, Nins, and here's a token of our appreciation for everything you've done for us here. Thank you. Round of applause.
Thanks,
Thank you,
guys.
thank you.